All right, so how are elastic and inelastic collisions different? Well, when we talk about collisions, we're talking about an isolated system again. We're going to treat them as isolated systems. And what do we know about momentum in an isolated system? If we have an isolated system, momentum is always conserved. That's a biggie. Momentum is always conserved no matter what if it's an isolated system. However, energy may not be conserved. And we just talked about why that was, didn't we? So if we have the first type of collision, elastic collisions, kinetic energy is conserved, momentum's conserved. Okay? Objects are going to bounce away from each other and retain their shape. All right? Conserved quantities, P and K. Okay? Momentum, P, little p is for momentum. Big K is for kinetic energy, right? Then we have inelastic collisions. So we have elastic and inelastic. In an inelastic collision, we have two possibilities. We have an inelastic and we have a perfectly inelastic collision. So two objects are going to collide and then stick, or two objects are going to collide and deform. It's got to be one or the other. So we have two possibilities here, A or B. Most collisions that we see are not going to be perfectly, are not going to be inelastic. They're going to, or elastic, they're going to be inelastic, even if they don't stick together, right? So we almost always, when two things run into each other, lose some type of energy. That's what happens. So what's conserved? Momentum is always conserved, isn't it? And that's it. Momentum only. Kinetic energy is not conserved. So the only type of collision where kinetic energy is conserved is if it is elastic. Hit, bounce off, don't deform. Think billiard balls, energy is conserved. Car crash, probably not. Now, perfectly inelastic collision, the object going to stick together and move as one mass. So in other words, initially, you'll have M1 and M2. That's in the beginning. And then you'll have M1 plus M2 at the end. So initial and then final state is they're stuck together. Make sense? And versus plus. So let's look at this. When two cars collide, energy is lost due to the cars deforming when they collide, right? We know that. Kinetic energy is not conserved, but momentum is. That's what makes momentum, the study of momentum, so powerful, is that even when energy is not conserved, because think about it, up to this point, we've been getting easier and easier to solve problems, haven't we? We went from kinematics, which wasn't so easy, there were a lot of equations and a whole lot of unknowns, to Newton's law, which seemed pretty simple, but you have all those free body diagrams and everything, right? To energy, which was even a little more simple because you only had to pay attention to the beginning and the end, but it was still bunches of different formulas, even if they were easier formulas. And now we're down to momentum. Momentum is simple. Momentum is m times v. How much easier can you get than that? The momentum you have in the beginning is conserved and you have the same momentum at the end. Okay, so this is the easiest way to solve problems if we can. So, energy equations from the last chapter can't be used. So when we can't, even when we can't use the energy equations, which are easier, we can use momentum. So, identify the following collisions as elastic or inelastic. Two marbles slide towards each other, hit each other, bounce away. Elastic, inelastic. Yeah, it's like billiard balls, isn't it? They bounce off to each other. So this one is elastic. Two rental cars driving 40 miles an hour on I-95 crash into each other and interlock together as they slide off the road. Elastic or inelastic? Not only is it inelastic, it's perfectly inelastic, isn't it? We know that because they interlock once they crash. Golf ball hit by a golf club sent flying through the air. Huh? Inelastic. Why is it inelastic? What happens to the golf ball? We talked about this at least once. it compresses some when the club hits it, doesn't it? It compresses and then it springs off, doesn't it? So it deforms. So this would be inelastic. All right, what about a football kicked by a foot, sent through the air? Doesn't the ball push in a little bit, kicking it? That's how the energy is transferred. So this is inelastic. 5 kilogram mass hits the wall with a speed of 5 meters per second, rebounds with a speed of 3 meters per second in the opposite direction. Why is it inelastic and not elastic? The wall doesn't move, but that's not why. I want you to look. What speed was it coming in? What speed did it go out? Did it lose any mass? But it slowed down, which means it lost kinetic energy, didn't it? If it lost kinetic energy, could it be elastic? No, elastic, remember, elastic is the only type of collision where it does not lose kinetic energy. So if it loses kinetic energy, it can't be elastic. It has to be inelastic. All right? So this would also be inelastic. Okay? Does everybody understand the difference between elastic and an inelastic collision versus a perfectly inelastic collision? And the big thing to remember is this one right here is the only one where P initial equals P final and K initial equals K final. That's the only one where momentum and energy are conserved. Now for this guy, P initial equals P final. For this guy, P initial equals P final. For this guy, getting the idea? So in all of them, we have conservation of momentum, but only the first one, that is elastic, do we have conservation of energy. Maybe if you write it enough times, it'll get in your head. So A is special. Are we good? Okay, so example B, we have to apply conservation of momentum. Conservation of momentum literally says the initial momentum equals the final momentum. That's what conservation of momentum is. So you'll be using this every single time. A 1,500 kilogram car going 20 meters per second rear ends it. 1,000 kilogram compact car going 15 meters per second on the ice the same direction. How fast did the two cars move together immediately after the collision if it is perfectly inelastic? So it's telling us it is a perfectly inelastic collision. So what we have to do is we have to think about this. First statement you should always start with solving these problems is P initial equals P final. Okay? So in the beginning, what do we have? And remember, you have to pay attention to signs here for the velocity because the velocity is a vector. We have mass what? Yeah, mass 1 times velocity of 1 plus mass 2 times velocity 2 initial equals, what do we know about the two masses in the end? They're together. So mass 1 plus mass 2 times the final velocity. That's what we know. Easy, isn't it? This is the easiest type of equation we've had to use since the beginning of this class. Momentum should be the one you'll love because it's really straightforward. So the initial mass is 1,500 going at 20. The 1,000 is going at 15. Now here's where I have to pay attention. What do we know? Same direction. What would I have to take into account if, say, one had been going this way and the other had been going the other way? One velocity would be positive and the other velocity would have to be negative. Just like with our cars. One would be positive, the other would be negative, okay? Equals, but they're both in the same direction, so they're both positive. Equals mass 1 plus mass 2 times the final velocity. Y'all find the final velocity for me. What'd you get? Anybody get anything yet? What'd you get? Yep. 18 what? Don't forget your units, please. Units are important. All right. Man of mass 1,500 kilograms jumps from a bridge onto a boat of mass 400 kilograms that's moving upriver at a speed of 5 meters per second. How fast is the boat moving afterwards? So we've got before, remember, P initial equals P final, right? So the initial state is what? What's moving initially? Is the dude moving initially? Mass of the man, velocity of the man, plus mass of the boat, velocity of the boat equals what do we know? Mass of the man plus mass of the boat times V final. All right, was the man moving it initially? Initially, he was standing on the bridge, wasn't he? Yes? So if he's standing on the bridge, what is his velocity? 0. So that's 0. Mass of the boat is 400. Velocity of the boat is 5. 150 plus 400 times V final. So find V final. What'd you get? Huh? 1 decimal place is fine. 3 point what? 3.6? Okay. All right. Example D, block of mass M travels at a speed 4v to the right. So mass M, speed 4v to the right. Collides with a block of 2m, traveling v to the left. After the collision, the block of mass M moves to the left at v. Find the speed of the other block after the collision. Is the collision elastic or inelastic? Justify your answer. So what are we going to have to figure out? Let's do A first. What's the first thing I always write? P initial equals P final. So initially, we have mass M times 4V to the right. So to the right means this speed is positive, doesn't it? We also have the mass of 2M traveling at V to the left. So what should I put here? Yep, negative V. It's a good thing I can read lips. Now, we don't know, we know mass M is moving, but we don't know what its final velocity is, do we? It's what it's asking. Plus, oh no, we do know. It's moving to the left at V. Excuse me, I messed that up. It's moving to the left at V, so what does that mean? Negative V, right? And then we know 2M, but we don't know which direction it's moving. So do you see how we can do this? So let's work this out. 4mv minus 2mv equals negative mv plus 2mv final. So I'm going to add mv to both sides to begin with, okay? Four minus 2 is 2 plus 1 is 3, so 3mv. Now what? What am I solving for? I'm looking for the final velocity, right? So if I want final velocity by itself, what do I have to divide by? 2m. M goes away. So the final velocity is equal to 1.5 times v, isn't it? Now, part B. Is the collision elastic or inelastic? What is the big difference between an elastic collision and an inelastic collision? In both of them, the momentum is conserved, isn't it? But in an elastic collision, E-L-E-A-S-T, in an elastic collision, what else is conserved? Kinetic energy. So we've got to see, is the kinetic energy, in other words, is kinetic energy initial equal to kinetic energy final? If the answer is yes, then it is elastic. If no, it is inelastic. So let's figure it out. What is K initial? Well, we've got two things moving in the beginning, don't we? We've got 1/2 4m, or I'm sorry, what is it? M. Hang on. Messing this up. Don't want to mess this up. We've got M traveling at what? 4v, right? And then we've got 1/2 2m times negative v squared. So 4v squared is what? 16v squared? And what is 16 divided by 2? So we end up with 8mv squared. 2, and the 2 1/2 goes away, so we end up with negative v squared, which just ends up as v squared plus mv squared equals 9mv squared. So now, K final. We're going to do the same thing with the final velocity, and m was moving at negative v, so 1/2 m negative v squared, and then the 2m was moving at what? 1.5 v squared. So this is 1/2 mv squared plus, what's 1.5? 2.25? So 0.5 plus 2.25 is what? So you tell me, does this equal this? No, it does not, does it? So if they don't equal, then what's the answer to my question? It's an inelastic collision, isn't it? Okay, so that's how we prove it. Remember this because you're going to have a lab later this week where you're going to be looking at that relationship. Do you have it or don't you have it? So we can compare, we can use momentum to find new velocities, can't we, in the collision? And then we can compare whether it's elastic or inelastic by looking at its kinetic energy, initial and final. So the answer to this one was no, since K initial was equal to 9mv squared and K final was equal to 2.75 mv squared. In other words, kinetic energy was not conserved, so inelastic. Notice the wording I'm using. I found the initial and final kinetic energy. I compared them and I said it was not conserved. That is an important thing to say. So if you were writing a quantitative qualitative, the quantitative part would have been the calculation, and the qualitative would have been saying, all right, I know since kinetic energy was not conserved that it's inelastic. It could not be elastic, could it? All right, so we good so far? In other words, kinetic energy was lost, wasn't it? We lost kinetic energy. All right, so let's look at this. A bullet is fired into a block attached to a rope of length L. Find the maximum angle that the rope is displaced. By the way, this is called a ballistic pendulum. Just so you know, this is a ballistic pendulum. Do you ever wonder how they know how fast a bullet is going when it leaves the barrel of a gun? This is how they can tell. This is how they used to be able to tell without like real sensors and stuff. They could measure how much they could shoot very close, boom, to a block that's suspended like this. Boom, what happens? The bullet's going really fast when it hits that block and is embedded, isn't it? It's an inelastic collision, so what happens? It goes up, doesn't it? It sticks together and it goes up. They could measure that angle and tell by how much it rises, how much the velocity change, because they would know the final velocity. Final velocity at the end right here would be 0, wouldn't it? So they would have a final velocity. They would have an initial velocity. They could figure out what's going on. So here we go. Let's look at this. We know that P initial equals P final, don't we? Well, in the beginning, what do we have? Let's do this. M1 V1 plus M2 V2 equals M1 plus M2 V final. Do you agree? This is M1 plus M2? Yes? What do we know about the velocity of mass 2 in the beginning? Guys, this has a velocity of V. This has a velocity of what? Guys, it's just sitting there. 0. So this is 0. So this zeroes out. So in the beginning, all we have is the velocity of the bullet, don't we? So this is M1V. It says M1 plus M2. That's the mass. And this is M1 plus M2 final. Okay? So now, we know that the final velocity of this block right after it hits, the velocity of the block right after the bullet hits it is what this is. Okay? So that is going to be equal to M1V divided by M1 plus M2. Agreed? We just divide both sides by M1 plus M2. Well, guys, now we look at it from the standpoint of conservation of energy. Notice I didn't say conservation of kinetic energy. This is an inelastic collision, isn't it? Is kinetic energy conserved? No. But mechanical energy is. Mechanical energy is conserved. In other words, mechanical energy initial equals mechanical energy final once the block hits. So in the beginning, we have what? U initial plus K initial equals U final plus K final. What is U initial going to be? Guys, we're looking at a block sitting here at the bottom end of a rope. Can we call that 0? So this is 0. It's going to be moving, isn't it? Final, it's going to come to a stop, right? Block goes up, comes to a stop. So this is 0. So I know this is going to be 1/2 what? M1 plus M2 V final squared, right? Because didn't we just say that's what this was? Plus M G H. We got to find out what H is. Guys, we've done this before. You may not remember it, but we've done this before. This length right here is L. What we're looking for is the difference between that and that. That is H. Do you remember how we found that? We called this a right triangle, and we said this is also L. Okay? And we said if this is theta, this is L cosine theta. This chunk right here is. So the other chunk of it would be what, L minus. Sorry, it's my son. Hello? Hey. Oh, did you get cleared? Woohoo! Yay. Congratulations. Yay, yay. Cool. Well, thank you. Yep. That's very exciting news. I'm so excited for you. Let us know what happens with your schedule. All right, bye. Sorry. This has been it was important. I knew that's what he was talking about. My son, like a year ago, you probably don't know because y'all weren't even in here. A year ago, my son, he's a firefighter. He's a fireman in South Carolina. Which by the way, uses a lot of physics, believe it or not. He slipped. They were playing softball with another group in their mandatory they have to do physical training. They were playing softball as their physical training, and he went to slide into home base and tore his patellar tendon. In other words, he tore the tendon that attaches your kneecap across your knee, and it slid up. So he had to have surgery. Well, he was recovering from the surgery, and somebody accidentally pushed him and he slipped again. It was a total accident, but they shouldn't have been pushing him. They pushed him, he slipped, he fell, he tore it, he retore it. So what went from a 6-month recovery became a year recovery because he had to have a second surgery, re-repair it, have a graft put in of a cadaver tendon, somebody else's tendon that they donated. And so it took a year from that point on and that was like 2 months into his surgery. So he's been off of his regular. He's been doing light duty for almost a year now, and he is ready to get back to being a fireman. He said light duty sucks. He does fire inspections on new construction. He hates it. He doesn't hate it. I mean, it's better than not doing anything, but he loves being a fireman and rescuing people. He saved people's lives before, so literally. So he's he just got the news that he's been cleared to go back to working. So I'm really tickled for him. All right. So does everybody understand that this chunk right here is L cosine theta, which means that this little chunk right here has to be L minus L cosine theta. The whole thing was L minus this chunk means H is L minus L cosine theta. We've done this calculation before. So what we're going to do is we're going to say this is 1/2 M1 plus M2. We know what V final is, don't we? Do you remember? We're going to take this and plug it in right here. So this is M1 V over M1 plus M2 all squared. This should be equals M. What is M? It's that M1 plus M2 again, isn't it? Times gravity times H, which we just said was L minus L cosine theta. Now, guys, this goes away and this goes away, doesn't it? Do you agree? It's on both sides, right? Mass doesn't matter. So now what do we have here? We are trying to figure out what? The max angle the rope is displaced. That would be cosine, that would be theta, wouldn't it? So let's get this whole thing figured out. So we have m1 squared, v squared, m1 plus m2 squared times 2 on that side. And on this side, we have GL minus GL cosine theta. So how do I get theta by itself? First thing I have to do is do what? Mathematically speaking, what do I need to do next? Guys, I got to isolate this term. So I have to get rid of that term. How do I get rid of that term? Subtract it. Minus GL, so minus GL. Now what do I need to do? Divide both sides by what? Not 1. I'm still trying to get cosine by itself because that's where theta is, right? So what do I need to divide by? GL. I'm going to divide by GL. Okay? So, let's look at what I have here. That goes away. So I have m1 squared v squared over 2 GL m1 plus m2 minus 1 equals cosine theta. And now, how do I get rid of the cosine part? How do I undo cosine? Guys, look at your calculators. What's above the cosine, directly above the cosine button? Inverse cosine. Isn't that what brings the angle out? Okay, so we simply have to do the inverse cosine. So theta is equal to the inverse cosine, m1 squared v squared, 2GL, m1 plus m2, minus 1. Okay? That is conservation of momentum in 1 dimension. I think we are done. That's in 1 dimension, isn't it? Okay, so what happens about, we'll talk next time about 2 dimensions. What do we do about collisions in center of mass and collisions in 2 dimensions? Now, what do you need to do before next time? 5-1, right? You got to watch the 5-1 video, and now you have 5-1 and 5-2 exercises to do. You've got about 7 minutes of class left, so I would use that time to do what? Start working on 5-2 exercises, maybe?